Thank you. Thank you for the invitation to come and speak. I was very sorry not to be able to be at yesterday's. One of the dilemmas of being a Dean of Medicine is you have responsibilities there, but I left early to get to dinner last night and I'm certainly here all day today. So what I want to talk about is adaptive trials, but I want to try to set it in a little bit of a historical context. And so, well, I think the very earliest trial I sometimes use for teaching is in the book of Daniel, where he says, I'm better off on a nice healthy diet. Let's try it out. But I think in modern times, one of the first trials that came of necessity was on scurvy, which people at ship were out at sea. It was a huge problem because it meant that the crew weren't fit to work. And the James Lint, who was the ship's doctor, sort of said, right, let's try to find out systematically. He had plenty of cases, gave them a mix of stuff. So some of them got seawater, some of them got vinegar. I won't go through them all, but 2 others each had 2 oranges and 1 lemon given them every day. And those 2 patients were rapidly better. One of them was sent back to his active duty, and the other one was recruited in as trial staff to help look after the other patients. I think it took a very long time before those learnings led to ships systematically carrying lemons and limes, which of course is what you need. But it was a comparative study. I mean, not an ideal randomized trial, but you've got to start somewhere. How do I? Okay. So one of the next trials, I find it intriguing because this was effectively one of the first trials of treatment, and it took place in wartime. And I think the motivation was worrying about a workforce who were being decimated by the common cold. And it was something called patulin. It had concurrent controls. This was not randomized, but it was concurrent. It didn't work. It didn't show any protective effects of patulin, which is probably worth knowing. But I think what it means is that trial is not widely recognised for his being a historic. But you can see the statisticians sort of limbering up, saying, we know how to do things properly. Okay, we can't get them to do randomisation this time, but let's go with concurrent controls. And then happy days. Tuberculosis, major problem. And a drug called streptomycin became available. But again, the question is, does it work? How do we prove it? What was the statistician's dream was that the supply was very limited. So you had to ration it somehow. And so actually a fair way of doing it is randomization. I think they made the argument that way. And so, I mean, the patients, from a modern perspective, the consent and everything was absolutely horrendous. But, we had 2 groups that were randomized and very quickly showed that this was a very good treatment. And so this is often celebrated as the first randomized trial in modern times. But, 1 year after the Second World War. So really interesting that, the thinking was going on. It wasn't a reason for not doing things. So why did statisticians know about randomization? Well, it wasn't a new idea in other areas. And rolling back and actually to just after the First World War, there were experiments going on at a place called Rothamsted, a sort of field station, to work out growing crops to feed people was important, getting better yields was important. So what fertilizers so on did one use, what seeds were best? And a young man called Ronald Fisher was appointed, and as I understand it, he was more or less given a pile of data and said, please try and make something of that. Some of you recognise that. And what he said after a while was, well, it's no good just analysing this data. You should have set your experiments up properly. And what he started doing was work on design. And the thing about crops is you sow the seeds, so you put your fertiliser on, but you have to wait months before they come up. So actually efficient trial design really matters. And so what he started developing was trial designs that allowed you in the same experiment to test out different aspects. So you might test out crops and the seeds and something else. And that led to design of experiments and multivariants. And I mean, he's a problematic character in many ways because of his later work on eugenics, but the fundamental shift in experimentation has really revolutionized agriculture. But it took a lot longer before that kind of thinking of let's be systematic about doing trials, not just one at a time. And it took a long while for that to percolate into medicine. And an early example, I remember being taught about this when I was an undergraduate, was in leukemia, where it's a very well connected, or at least the children's leukemia, as I understand it, was a very well connected medical establishment. And what they started doing was saying, right, we have lots of uncertainties. Every child who comes in to a clinical setting will be offered randomization on the aspects we don't understand. And so what you see in that graph is in the 1970s. So actually, that was, well, I remember one of my school contemporaries died of leukemia. It was in that period. And the bottom line is the children who didn't go into trials, and the top line is the children who did. And there's a difference of sort of about 20% survival by the end. Now, that's not an unbiased comparison. Clearly, the children who went into trials are not necessarily comparable to the ones who didn't, but it's indicative. But the next slide shows the shift from the 1970s through to the beginning of this century, going up from a sort of long-term survival of about 40% to a long-term survival of about 90%. That is game-changing, impact case study, hands down. And that, as I understand it, was achieved by the community systematically experimenting, feeding that back in and experimenting again. So it was, I mean, I'm not sure it was an organised platform trial, but it was definitely a very organised approach. But as far as I know, that didn't happen in any other clinical areas, despite that brilliant evidence of what can be achieved. So turning to a slightly different tack, other things that were going on during this time was that statisticians were having long-running debates about whether one was a frequentist, and actually Fisher did some sort of funny things with p-values that sort of still influence how many people do things today. And then there was another kind of tribe who said, no, you need to be Bayesian. And I'll explain a bit more about what that is in a minute. And it was all very, very polarized and actually got quite nasty in some of the discussions. And the computation wasn't up to doing any really interesting problems. But what began to happen was that some statisticians started playing with it and just being more pragmatic. And three, who at the time they started the work were all based in Cambridge, David Spiegelhalter, Larry Friedman and Max Palmer. Larry then went off to Bethesda and I think is now in Israel. They did work to start to say, what would it mean if we took Bayesian approaches to randomized trials? And there have been quite a lot of papers, but it came together in this Royal Society Red paper in '94. And there's lots of discussion in it, so you can see people's thinking at the time. But what did they... Well, first of all, who was Thomas Bayes? We don't know much about him. He was a clergyman, nonconformist, and those were kind of the academics of their generation. They did their thinking. The plaque on that house claims he lived there. Andrew Keatley looked at my slide and said, well, they're not sure about that. That is his grave. It's engraved on it. I mean, I think it's unlikely that he's not buried in there. It's a kind of family grave in Bunhill Fields, which is where the nonconformist people got to be buried. And that is the picture which is classically used of him. Again, I think there's a lot of uncertainty about whether this particular picture was really him, but as a clergyman, that's certainly what he would have worn. But the key thing was that he did mathematics and came up with a sort of approach to probability. He didn't publish it. It was his friend Richard Price published it posthumously in the Philosophical Transactions of the Royal Society. And about the most scary thing about being elected, apart from having to go and talk to the other fellows in 5 minutes to explain the work you do that you're elected for, is they then say, oh, and by the way, we'd like you to write a paper. So anyway, his work was published in this. And in its original form, it's pretty indigestible. The form in which I met it as an undergraduate was as a essentially conditional probability. The probability of B given A can be turned into the probability of A given B. And that is the underpinning of sensitivity and specificity calculations, for example. I mean, I haven't put up the sort with the integration sign on that has the continuous version. But the key thing is that this is sort of in Bayes' world, this isn't just about sort of probability events. So what's the probability that one of the dice is a 6 if the sum adds up to 12? This is looking at what happens if we've got some alternative explanations or hypotheses. So what's the probability that this drug treatment, that this person gets better if the treatment works, versus the probability if they get better if the treatment doesn't work. So we've got two hypotheses, one of which is the treatment works and one of which doesn't. And I find it easier to think about these graphically. And so for a clinical trial, you could think of this as the improvement in survival rates. You could think of it as definitely the probability. You could think of it, if you're into blood pressure trials, as the increase in blood pressure. But generally, before we start a trial, we actually have some idea or knowledge of what that estimate might be. And we could, on the appropriate scale, say what's our best guess, what's the uncertainty around it. We then go and collect some data, and we get a slightly different estimate and maybe some reduced uncertainty. And what Bayes' theorem does is to mathematically sort of mix those together and say, well, blow me if what we think afterwards isn't somewhere between what we thought before and where the data was. But generally, or not generally, mathematically, the uncertainty is reduced because that's the way the calculation works. So the question is, how do we use that? I mean, mathematically, that is tractable, and certainly I've set it as an exam question for third-year students to do on a hand calculator. So let's look at an example, which was a trial I was involved in, and actually David Spiegelhalter and colleagues borrowed for that paper of theirs. And it was looking at two sorts of radiotherapy for cancers in the pelvic region. Photon was the standard, and the idea was that neutron were bigger and therefore would sort of target more effectively. They looked at morbidity and mortality. I think not expecting much change in mortality, but morbidity might be better. Planned for 400 patients. And at the point I got involved in, and so the question is, what did we think prior to that? What does the data say? And how does that all mix together? So where might we get priors that are appropriate? Well, Sheila Bird, who had been involved in this study, did a meta-analysis of low-energy neutron therapy. This trial was high-energy neutron therapy, so you can argue about whether it's relevant, but it's not a bad place to start. And then she'd also documented what the clinicians thought, because she thought it was important to know whether they were in equipoise or not. And I won't go through the details of those calculations, but essentially, the low-energy neutron therapy hadn't worked. To the left-hand side of that graph, what that means is this treatment does not work, whereas the clinicians prior was slightly optimistic. And the key thing is those goalposts between what I've marked as naught and there are the region of equivalence. So she'd also got the clinicians to say, what do you think you would need to use this routinely, given it's an expensive treatment and you need a big bit of equipment? And so she translated that from what they said into the log hazard ratio scale, which, if you were wondering what the numbers were, it's on that scale. And so you've got a region of equivalent. And she was satisfied that although they were fairly optimistic about the treatment, they were still in equipoise about it. In other words, most of the weight is between the goalposts. Whereas the low energy neutron therapy, they'd stopped doing the trials because that very clearly didn't work. So if you then mix in the data from this trial, what happens? Well, the first thing is to look at the data. And this was an interim analysis, but the neutrons are the new treatment, and that survival is worse than photons. And that is why we do trials. I mean, Sheila had also spent a long time arguing for them doing trials at all, because they just wanted to start using it. And clearly, at least on the face of it, people are dying at a rather faster rate. So it becomes very important to look at that and say, well, how seriously do we take this at this point? Do we carry on randomizing, or do we stop? And so if you mix that in with what is effectively a skeptical prior from the low energy neutron therapy, the combination of that plus this new data means that you are a long way to the right. You are outside those goalposts, and you really ought to stop randomizing. There's nothing between the goalposts, so there's no equipoise. Whereas if you do it in the light of the clinician's prior, you've got some equipoise, but there was no data monitoring committee in place. We're coming onto those in later, but we pulled one together and they looked at this data, not using this methodology, but the same argument. And effectively what they said is there is no chance of this treatment being good enough to be used routinely. So actually, there is no point in carrying on randomizing. And those who are saying, well, you have to, your p-values aren't where they should be. No, if it had been the other way, you'd have carried on for definitive evidence it was better. But there's no point in randomizing if there's no chance of this being good. So anyway, those trials were stopped, and we had the data to play around with as illustration for Bayes. And I mean, I'm on the slides are the formal levels of probability, but I understand it better visually. So that's a simple version of Bayes, and we'll come back to it. But I've mentioned data monitoring committees, and I think they were used fairly routinely in the pharma industry at that point, but they certainly weren't being used routinely for publicly funded trials. So why do we have them? Well, the clinical trial is a rigorous, usually randomized test of efficacy and safety. And for most of my career, this has been about two group trials. Whereas with the agricultural trials, it's very easy. You sow all your crops at once, you water it, and then you leave it, go off and have your summer, and then you harvest it and weigh it and then turn it into beer or bread to celebrate. Patients, they won't do that. They're complete nuisances. They won't all turn up ready all to enter the trial on the same day. They come along, they get diagnosed at different times. And so what you do is start them when it's appropriate in their clinical journey. But what it means is that we start to get information on some patients before we've randomized some of the later patients. And if that was me, I'd be thinking, well, haven't you learned something? Don't you know now what's the answer? And so there's real questions about whether it's ethical to carry on randomizing. If you do stop, what do we do for existing patients? And so the construct we normally use is what's called a data monitoring committee. They review the data in confidence, and they advise on whether recruitment should be stopped or sometimes modified. So the question is how you make those judgments. In hindsight, the neutron therapy looks easy, but there was a huge amount of agonizing at the time. And so classically, we've had statistical rules to help us. Group sequential, often frequentist, and I'll go through a couple of those, but Bayesian approaches are available. And the point I want to make, because it's relevant later, is they are typically just based on one efficacy endpoint, not more, and safety is addressed rather less formally. So what do they do? Well, the trouble is, if you kept just testing at a 5% p-value, just by chance, it might bounce above that. So, in fact, my PhD supervisor, Stuart Pocock, did an early version of this, and he said, well, if you can do 5 interim analysis for the sake of argument, you can spread your p across that, and if you multiply those together, overall, you've got an error rate of 5%. But you can see the downside. You get to number 5, you've got a p-value of 0.03, a very excited clinician, and sorry to clinicians in the audience, I'm stereotyping you slightly. And you say, no, you can't claim significance because you'd spent your p earlier. So that doesn't feel quite right. You had Richard Peto, who was make it large and then carry it on till the end. So he used the same thing, but he said, you don't have to do it equally. We'll give you a tiny smidgen at the first 4. And then effectively at the last one, you've got a p-value that's almost the same. So we've got, one porridge that's too hot, one that's too cold, and of course O'Brien and Fleming came up with the mummy-sized one that's just right. And so tiny amount at the beginning, there's no chance that with a very few patients you're going to hit that. But as time goes on, if you've got a very good treatment, there is a good, reasonable chance you might stop early. So they're all nice and objective. The only subjective thing is on which one do you choose? Because they come up with different answers, and that's a refrain that you'll hear a bit later. And actually, there's a very nice paper by David Biggerharter and colleagues showing that each of these is equivalent essentially to a different skeptical prior. And so you could say the choice between these sort of means which of those priors do you want to be using to guide your decision making? But what I was interested in was trying to get these into practice. And I was asked to sit on a data monitoring committee for a trial being run out of what was at that time the Cancer Trials Office in Cambridge. And it was pre-operative chemotherapy to shrink the tumour, which then made the surgery easier. And primary outcome was survival time. So I worked with the trial statistician, Peter Fairs, and we wrote to Max Palmer because we don't quite know how to do this. So Max came and talked us through it. So the question is, how can you use this formulation for data monitoring? And what you do there is to make sure that your prior is deliberately chosen to be skeptical. We set up trials because we don't know. And even if you're really enthusiastic, there'll be a community out there. It might be that, you think there's regulators, it might be your clinicians in another centre that have got another favourite way of doing things. So you can conceptualize this as you need to overcome that uncertainty. You collect your data, and then if it's shifted enough, you can make your decision. And so what we did was to step through this, and I won't go through the details here because I want to get on some other things, but a couple of key things. This was one of the first trials where Bayes was used in real time. So what we did was a lot of scenarios where we worked through with the other members of the Data Monitoring Committee what this means. If the data comes through looking like this, what are the implications? We negotiated with them what the stopping guidelines might be. And we actually wrote that up in Stats in Medicine as a tutorial paper. And it's very well cited, I think, because Max helped us see it clearly. We then use these scenarios to write it as a paper. And the trial ran its course, and that's published later. But that was where things were for a long time. But Bayes really comes into its own with complexity. And so 2 trials I want to just pick as exemplars that were sort of, if you like, in the spirit of Rothenstedt and the leukemia trials of trying to be efficient. One was a Women's Health Initiative trial, which was looking at multiple things that affect postmenopausal women. And I'll show you a little bit more detail, but essentially it deviates from the standard 2-group trial because there are multiple treatments and multiple endpoints. And then Stampede, which is an adaptive trial that I think Thomas might have mentioned yesterday, which is setting up a sort of platform that says, at any one time, you'll be offered randomizations appropriately, but as we learn about the treatments, the things you're being offered will change. So one of the complexities for data monitoring is when you've got multiple endpoints, because none of that stuff I've just talked about can deal with more than one endpoint. It can arise in treatment trials. It arises a lot in prevention trials. And so the question statistically is, what do you do? Do you use composite endpoints, which is kind of what cardiovascular trials use? They add together the heart attacks and the procedures. Do you use some kind of hierarchical testing? Do you use some kind of essentially economics approach of trade-offs and weightings and find out what patients actually care about and factor that in? So with the Women's Health Initiative trials from the States, it was a factorial trial, but you were offered the randomizations appropriate to you. So one of the treatments was hormone therapy, and that at the time they were looking at to try to prevent heart disease. But you needed to look at things like hip fracture incidence, breast cancer incidence, and so on. The second was dietary modification, breast cancer incidence being the primary outcome, but colorectal and other things were of use. And then calcium plus vitamin D for hip fractures. But again, you have to look at the other endpoints. And Lawrence Friedman was involved in that. And he did a really nice paper where he said, well, how do we do this with these multiple endpoints? You can use total mortality. You can use just specific approaches. Okay, for each of these randomizations, we'll look at the primary outcome. You can do unweighted combined indices, just add all the events together. You can do weighted ones. You can do weighted with Bayesian monitoring. He did a lot of scenarios with the DMC because it really matters. With the 2-group trial, it's kind of easy. Whereas when you've got all of these weightings going on, whether you should stop or not is really difficult. And the thinking they did with those scenarios, I think then helped to inform their choice. And again, the paper goes into all the details of that. But what I took away from that was when things get complicated, you actually do need more formal guidelines because it's just impossible to get your head around it. The second complexity is multiple treatments, which you can get in combination therapies, which we had there. They arise increasingly in the context of platform trials. They arise in umbrella trials, adaptive trials. And Stampede is the example, which is a sort of classic one in prostate cancer, where lots of treatments were started off, most of them were stepped down, one of them became standard, and then they brought in others. But again, how do you do the data monitoring committees? How do you do the comparisons? It's really quite a challenge. And there's been a lot of thinking about adaptive trials. And back in pre-pandemic, I was asked to chair the Academy of Medical Sciences, had what they call a forum, which is bring together regulators and academics and industry. Not to say about the science and the statistics of them, that's fairly straightforward, but what are the logistics? What are the funding models? What are the models about ownership of, who leads on which aspects? How do we share credit? And we had Stampede as an example, focus for metastatic colorectal cancer, something in Alzheimer's, and Alice, where I've been on the data monitoring committee, wonderful, beautifully elegant trial in influenza medication to work who they worked for. Trouble is that we missed the first wave because they were still faffing around with the design. Second wave was small, and the third one wasn't really enough, and then it all went away. So, like a wonderful car, but you've missed getting into the racing track, so you would never actually get to demonstrate it. But come the pandemic, I got a call from the same team saying, will you sit on a data monitoring committee? And that's because that team looked at Principle, and I'll show you some of the outcomes of that, which was a platform trial for higher risk patients in primary care. Recovery, which again, I think you heard about yesterday a little bit, was in the hospital trial. And REMAP CAP was the critical care trial. And the phenomenal thing about that, when you think how complicated these trials are, they'd only identified the treatment in the COVID in January. By April, all of those trials were up and running. I mean, I think that is a phenomenal achievement. And actually, the pre-work on Alice meant that we were ready to run on these. So 49,000 patients in recovery. The red treatments are the ones that were stepped down for not working. The green ones came in very early on. Dexamethasone started being used routinely, for example. REMAP CAP. So recovery was the Oxford group, and so they used classical methods. I mean, you can manage to use them somehow. REMAP CAP used Bayesian adaptive platform trial. That was led by my colleague Tony Gordon at Imperial. And that stepped down ineffective treatment in the March. Dexamethasone and other corticosteroids improved recovery. And I mean, these have saved thousands of lives. 18,000 for the COVID randomizations in 10,000 patients. So very complex trial, building on something that was up and running, and they COVIDized it. And actually doing this in the community, I think in many ways, this was a more groundbreaking trial, 12,000, just phenomenal. Again, I've said all of these are in times of need and mainly ruled out treatments. But when you think how much money would have been used if we'd been giving azithromycin routinely to people going to their GPs, and actually the only one that does work is an inhaled asthma treatment. So I was chairing the data monitoring committee. We started off meeting every couple of months, every month. At the peak pandemic, we were meeting weekly. I mean, I had lots to do during the pandemic because I was running the School of Public Health at Imperial. We had teaching going online, but this is what kept me on my toes because the data was going off every week to Berry consultants in the States. They were doing their Bayesian models. It was coming back and we were making decisions in real time. We were grappling with two primary endpoints because initially they wanted death rate, and hospitalization, but actually they also had time to recovery in there. And there was this gatekeeping strategy, which actually, I think, made some assumptions about those first two being linked that turned out not to be terribly true because there were different processes going on. We had multiple treatments. We were adding in treatments, dropping them. And they had a Bayesian model with a time machine component. And every now and again, I got assured that the Bayesian model was dealing with all of this. And I'm afraid I'm cynical enough to say, well, can we see some sensitivity analysis? What assumptions are this making? Because there are some deep-rooted things there. We had to update the rules to reflect the evolving situation. So we did sensitivity analysis. The adaptive randomization ratios are potentially informative. So when it came to releasing data, normally when you release from a data monitoring committee, you put everything out there. Here, the reservation was if you tell them what the numbers are in the groups, that will tell them something about the treatments that are still going on, because statisticians are quite good about reading this stuff. How much data you can't release the control group data. So there were some really interesting things that I hope will keep generations of PhD students sorting that out. But perhaps my practical conclusion on this is you may think this won't be me, be you a statistician or be you a clinician or maybe a lay member. Below me, we have lots of data monitoring committees going on, and you may well find yourself on one of these at short notice. So check you understand the purpose of the trial. Check you understand whether there are formalized guidelines, whether there are informal guidelines. And even if you've been on one trial, the second trial may work in quite a different way. The US has different conventions to us. The Berry consultants had assumed that we would automatically feed back the randomization ratios to be changed, because that's what happens in early stage trials. But in a late stage trial, the data monitoring committee have to advise the TSC of certain things. Complex trials, different approaches can yield very different results. And so the pre-work, the thinking it through is absolutely vital. Clearly in a pandemic, we didn't have time for so much of that. But in general, you do, all that time that people are trying to recruit patients, you've got time to do your pre-thinking. I would say Bayesian approaches are coherent and flexible. What I haven't emphasised is that changes in computation mean that we can now do the Bayesian calculations for these big complex problems in ways that we just couldn't when I first started playing around with this. And if you are the statistician, A, you need to understand it. And secondly, you'll be the one communicating, because as soon as they get these graphs and those funny numbers, they turn to statisticians and say, what does it mean? Well, what do you think? And so the communication aspect is absolutely key. And other communication about what are the communication lines between the DMEC and the trial steering group often need to be established. So just, never assume that you're not quite understanding and someone else is on top of it, because it's not a safe assumption. So just to finish, the interesting thing for me about all of these trials is that they were born out of necessity, often wartime or pandemic time, which was very similar in many ways. You can do difficult and new things under those circumstances. Trials are now becoming much more efficient, but there's a complexity. And Bayes, I think, comes into its own when there is complexity. But I think adaptive approaches have come of age. This is no longer, in the playground of PhDs that you examine and think, oh, well, I can't see that going into practice. This is now real life. But I shall stop there, and if I've managed to leave any time for questions, I'll happily take any. Thank you.